Hi everyone, welcome to the Astronomy Public Tour. Our speaker today will be Miranda Jarvis. And before we get to our talk, I just want to do a little bit of advertising for a associated event, Astronomy on Tap Toronto. So they're going to be having an event on February 18th. And this is an opportunity for you guys to listen to some astronomy and talk to some astronomers in a comfortable setting. It is in a pub, so it's a 19+ event. And please go to our website, universe.utron.ca, for more information. So our talk today is by Miranda, and she is a first-year grad student at UofT. She actually did her undergrad here at UofT, so she's been with us for a while. And Miranda's dream job is to work on a spaceship as a science officer, but
Starship. It's much cooler.
And since she can't do that, she settles for studying galaxies. So Miranda's interested in how galaxies are created, how they evolve and behave, and she's interested in using different techniques to observe these galaxies. So on her free time, Miranda also is part of the varsity fencing team and a Girl Guide leader, among other interests. So let's give a round of applause to Miranda.
All right, let's switch to the other show. All right, so thank you guys for all coming out today. And for the next hour or so, I'm going to take you on a journey through the Milky Way and try and give you a bit of an idea of what it looks like, what it's made out of, and how we have any idea about any of that. So if you've ever had the chance to go outside on a clear night somewhere far away from the city lights, you might have been able to see a view something like this, with the Milky Way spread out above you as a sort of white smear across the sky. So these days, seeing this beautiful view is actually quite rare. With all of the city lights and electronic and light pollution everywhere, it's really hard to get anywhere that isolated. But in the ancient times, before all of our modern technology and we really started to light up the world, this was a common sight. So the Milky Way is central in a lot of mythologies from across the world. So the ancient Greeks thought that it was a stream of milk spilt from the breast of the goddess Hera by Hercules, the son of Zeus. So some of the Native American tribes believed that it was a road that dead warriors would travel to the afterlife. And in China, it was thought to be a river that was separating two lovers. And of course, ancient philosophers had a lot to say about the Milky Way as well. Aristotle thought that it was vaporous clouds from Earth that would block out the light from the stars. And it wasn't until Galileo pointed some of the very first telescopes up at the Milky Way that we saw that it was actually made up of millions of individual stars. So when we look up at the Milky Way at views like we saw earlier, we're using just a very small expanse of the electromagnetic spectrum. So the electromagnetic spectrum is light in its entirety. So what we see with our eyes, they're playing with the lights, is this part. So which, as you can see, if we go from all the way on this end, which is cosmic rays, which are very high energy, short wavelength light, all the way over to this end with the radio waves that are really long wavelength and low energy, the light we see is just a teeny tiny fraction. So astronomers, rather than limiting ourselves to the sort of light that just happens to be what our eyes are sensitive to, we like to look at the sky in lots of different types of light and see what we can learn about different parts of the galaxy and different things in it. So we'll start by looking at an all-sky map of the Milky Way in optical light, so the light that our eyes see. So this is a lot like what we saw on some of the earlier slide we had, but it's showing the entire sky at once, unlimited by horizons. So the next few slides I'm going to show to you are all images that were compiled by NASA. So one of the things you'll notice in this one is there's all of these dark patches running across the galaxy. Those are caused by clouds of cool dust and gas that are blocking all of the starlight from behind it. So now we're going to start at the very far end of the radio continuum, so the very long wavelength, low energy light. So this is caused by clouds of very hot ionized gas in the space between stars. So it forms this really poofy, big clouds. One thing you might see is this sort of spot jetting up. That's called the North Polar Spur, and it was caused by a supernova that exploded quite near the sun. So now we're going to step into slightly shorter wavelengths. This is molecular hydrogen. So it's caused by cooler dust. And as you can see, it lies in a lot thinner space than that hotter gas we saw. So this molecular hydrogen, these clouds, are the sites of star formation. So next we have the infrared. So this is the type of light that you'd feel as heat and that a lot of the fancy night vision goggles will see in. And so in this sort of light, what we're looking at is actually the emission from the dust. So the same dust that in the optical blocked a bunch of the starlight, in the infrared, it's shining out bright for us to see. So now we're going to the near infrared. So this is just sort of a small step redward of the light we see with our eyes. And in this band, the dust doesn't do anything at all. It's not shining, emitting, and it's not blocking the starlight. So we're able to see the light from the stars for a lot farther than we can in the visible light. So finally, skipping over the optical light that we've already seen, we have the X-rays. So this is high energy light. So a lot like how we saw in the visible light where the dust was blocking a lot of the starlight, the same thing happens in the X-rays. So this dark band here where the disk is it's dark and cool because most of the X-rays can't get through the dust. Where if we go a little bit above, we see a lot more X-rays. Again, we can see the North Polar Spur in this image, the same as we could in the radio. And there's also some small bright patches, which you might not be able to make out, but those are caused by more distant supernovas. So how do we go from images like this, which are mostly flat, we have these disks, and how do we go from an image like that to something like this, which is a precisely mapped out picture of the Milky Way from above, where we have spiral arms, we have this bar in the middle. How do we even get to something like this, which to the eye looks about the same shape, especially in the near infrared. You could really see the disk and then that bulge shape. But how do we know how big it is? How do we know where the sun is in relation to this disk and what the different parts are? So I'm going to try and show you some of that today. So like every good journey, we need a map. So this will be our map for tonight. We'll start by talking about the disk, how big it is and what it looks like. So it's 100,000 light years across. And as we meander across this disk, we'll notice that it's filled with dust. This dust has some different forms. It can be in dense clouds that block out all of the light behind it, and also just in thin, vaporous mists that just serve as a screen between us and the distant stars. The disk is rotating, so it's spinning at about 200 kilometers a second. And if we look closely at how it's rotating, we know that it's embedded in this giant cloud of dark matter, which we can't see or feel. It doesn't interact other than through gravity. We know that the Milky Way has a bulge. If we look back, that's made up of older stars than those that form the disk. And of course, it has those beautiful, iconic spiral arms. So let's take a step and start our journey. So we have the disk, and it's 100,000 light years across. So just in case you don't know or you've forgotten, a light year has to do with how far light can travel in a year. So 100,000 light years means that it would take light 100,000 years to go from one edge of the Milky Way to the other. So the first person to really try and map the Milky Way was William Herschel in 1781. So this was before they'd invented cameras at all. So when he was trying to map the Milky Way, he was doing this all by eye. So what he did is he looked in every direction and counted how many stars he could see, and assumed that there was nothing there to block the light. So to try and figure out how far they are, he used a simple idea that if all of the stars have the same brightness, that a star that looked dimmer would be further away. And you can sort of visualize this by using a candle that has the same brightness, but if you put it farther away from you, as these go, it gets a lot dimmer. And so he was more or less right. This distance stimming thing is very true, and for the most part, the stars he was looking at would have all been about the same brightness, because although stars do vary a lot in how bright they are, the brightest stars are about all the same, and with his naked eye, he would only be making out the very brightest stars. So another way to think about how the light varies with distance is a bit more technical, but might work for you. So if you have a light bulb, it's shining out in every direction. And if you're really close to it, that light only has to fill sort of a tiny sphere. But if you're looking really, really far, that same amount of light that the bulb or the star is sending out has to fill a much bigger region. So on this diagram, we have this little square here that has a bunch of light going through it. But that same light, if we step a little farther away, has to fill 9 squares. So you have the same amount of light spread out over a greater distance, and so it looks dimmer. But William Herschel wasn't able to put any numbers on this map. He could tell that stars were dimmer than other stars, and from that tell that they were farther than other stars, but he had no way of measuring any of these distances. So he couldn't get any idea for the actual physical size. So for that, we had to wait more than a century for a man called Jacobus Keptine and the observation of parallax. So parallax is something that people have known about for a long, long time, since the ancients. And you can see it really easily. So if you put your finger in front of your eyes and sort of try and line your finger up with something in the background, so like the clock on the board or maybe the sun in my diagram, and then you close one eye and then the other, you'll notice that your finger will move compared to that background. And that's something you can see if you're driving in a car. Trees will seem to move compared to mountains. But when we were looking up at the stars, so the ancient Greeks looking at the positions of stars, they never noticed this. They couldn't see some stars moving with respect to the background stars. And so that was used as an argument that the Earth was still, actually, for a long, long time. Because if the Earth moved, you'd expect to see parallax. But the problem is that the distances are so very big. So this diagram is kind of misleading. So the idea is, just like when you change which eye you're looking through to see your finger move, when the Earth moves around the sun from June to December, our perspective changes. So this nearby star, which in our what we just tried, our demonstration, would be your finger, would seem to move compared to these background stars across the year. But these distances are very misleading. So the distance between the Earth, that the Earth moves around the sun, compared to the distance to even our nearest star, is something like 50,000 times smaller. So you'd have to expand this diagram to be way past the board. And the angles that you would see in the change of the distance would be very, very small. So we needed very good telescopes and also the aid of photography before we could have any chance of seeing parallax. So by about the early 1900s, when Keptine was observing, they'd be able to see the parallax of about 12 stars. And because we know how far the Earth is moving over the course of a year, we can use that to calculate an exact distance to these stars. So now that he knew the distance to some stars, Keptine was able to use the exact same methods that Herschel did earlier, where a star that's a certain amount dimmer than a star you're looking at must be a similar amount farther away. But now, because he had the distance to even just those few stars, he was able to calibrate those measurements and come up with a distance. So Keptine's model for the Milky Way looks a lot like Herschel's. This is actually just overlaying on Herschel's model. But he was able to put that big number on. So he said that the galaxy was 50,000 light years across. So if you remember from the beginning of this section, I told you that the Milky Way was 100,000 light years across. So Keptine wasn't quite there, but he had put a number on it, which is pretty impressive. So this sort of techniques is something that's still really prevalent in astronomy. So this is a bit of an advertisement for the Gaia Mission, which is a satellite that was launched in 2013 by the European Space Agency. And its goal is to measure the parallax and positions of 1 million stars to very, very high precision, and to gain a much better map of the Milky Way than even we have now. So if you compare that to the sort of 12 stars that Keptine had parallax on, this is pretty impressive. So at about the same time that Keptine was coming up with his measurements for the size of the galaxy, another young man was trying to do the same thing. This man was Harlow Shapley. So rather than counting individual stars like Keptine did, Shapley took advantage of these things called globular clusters, which are really dense collections of tens of thousands of stars that form these balls that are found scattered through our galaxy. And to measure the distances to these globular clusters, he constructed what astronomers call a distance ladder, which is a technique that's still used a lot today. So the main idea of a distance ladder is you have some way of measuring distance. So for Shapley, he started with parallax. And then you use that distance, that measurement, to go as far as you can. But there's limitations. So parallax, for example, only works for very, very close stars to us. So, but then you can use the one distance that you know how to measure to calibrate a new one. And therefore step up the ladder, where each step, each rung, is used to calibrate the next and to get measurements. So you can work your way out, but each step is worthless without the ones below it. So let's try and look at Shapley's distance ladder a little bit more closely. So we start with parallax, which we've already explained with the movements of nearby stars. So from these very few nearby stars, we were able to figure out something called Cepheids. So Cepheid stars are very cool because they expand and contract on a very regular time scale that ranges from a couple of days to sort of 50 days. And if you look at how quickly they oscillate in the period of their growing and shrinking, it correlates really closely with how bright they are. So on this plot, we have how bright the star is versus how quickly it cycles through this growing and contracting phase. So for example, if you see a Cepheid and it oscillates at 5 days, you can go up and see it's about 1,000 suns bright, or as bright as 1,000 suns. So if you know how bright the star is, and you see how bright you see it on the sky, then you can find out how far away it is. So Shapley had a handful of globular clusters that he had these Cepheids in, but that handful wasn't good enough for him. So he went up to the next rung of his distance ladder, which is our Lhari Stars. So these are stars that are a lot like Cepheids. They have a similar period luminosity relation, but they're a little bit dimmer and their slope's not quite the same. So this is a completely different type of star with similar behavior, but there aren't any of these near the sun, so we're not able to figure out how bright they are using parallax. But some of the globular clusters that Shapley measured the Cepheids in also had our Lhari stars in it. So because they're in the same glob of stars, you know they're at about the same distance as those Cepheids. So if you know the distance to the Cepheid, you know the distance to the Lhari star, and so you can find out how bright it is, and use that to expand to globular clusters that don't have any Cepheids in it. So from then, he had a much bigger collection of globular clusters that he knew how far they were. But that wasn't good enough. So from there, he noted that all of the brightest stars in all of the globular clusters that he did know the distance to had about the same brightness. So he used that a lot like Herschel did to find the next ones. So if the brightest stars were dimmer, he knew it was that much farther away. But that only works as long as you can make out even the brightest stars. But as the clusters get farther and farther, you start to not be able to see stars at all. So from there, he noted that the sizes of all the clusters seemed to be about the same. So if he saw a cluster that was farther away, or that was smaller, he knew it was farther away. So you can see the same thing with these candles. So the first one is really bright, but it's also about twice as big as this one. And as they get farther, they get smaller. And so from that collection of different methods, Shapley got a number for the size of the universe that was 300,000 light years across, which if you compare to this little white blob, which is Shapley's universe, or Kepting's Milky Way, it was a lot bigger. So one thing, if I say universe, it's actually really cool, because at the time that these guys were making these measurements, they actually thought they were measuring the size of the universe, where now we know it's just the Milky Way, it's just one of a lot of galaxies. So we have a size for our galaxy, but neither of these is quite right. So to actually figure out how to get from these two contradictory measurements to something that's a lot better, we need to move a little bit farther on our journey. So let's talk a little bit about dust. So it seems really obvious that there's dust in our galaxy. If you just look up, even with your naked eye, you can see these dark patches. So astronomers back in the early 1900s, they weren't fools. They could see these dark patches as well. But they could also see things like this. So this is the Orion Nebula. So it's filled with dust and gas, and it's super bright. So it's pretty hard to miss on the sky. So they figured that if you look at a patch of sky, you don't see something like this, and you see stars, that those stars, there's nothing between you and them. You can't see the dust, you can't see the gas, you're good. And so that's why people like Kepting were able to just look at distances and say, all right, it's dimmer, it's farther away. But Robert Trumpler sort of changed all that. So in 1930, he decided to do a similar sort of survey as Shapley had done, but rather than using globular clusters, so these dense collections of tens of thousands of stars, he used open clusters. So this is the Pleiades. It's one of the most famous open clusters. And open clusters just sort of a few thousand stars, so they're a lot smaller. And he measured their distances in two ways. So first, he measured their distance based on how big they are. So the clusters that were smaller were farther away. And then he measured them by how bright they are. So the clusters that were dimmer must be farther away. And you would expect these two methods to match. So if you measure the distance one way, you hope to get the same answer as if you measure it in a different way. Then that would lead to this straight line that he predicted. But Trumpler didn't actually see that. He saw this line that sort of curved. So the distances he measured from their brightness were bigger than the distances he measured based on their size. So that's kind of weird. So when we look at this picture, we see that clearly the farther away you get, the smaller you get, and the dimmer you get. But the other way you can explain this is if you put something in the way. So this one, it stays the same size, but it gets dimmer. So the size doesn't change, but the brightness does. So by doing this, Trumpler showed that there is dust and that it lies in this disk. So all of the open clusters that Trumpler looked at lay in this region. So what we now know as the disk of our galaxy, where all of the globular clusters that Shapley looked at, or most of them at least, were way above or below the disk where all of the dust lies. So when he measured his 30,000 light-year Milky Way, he did it using globular clusters, so dust wasn't a problem. Where Keptine, looking at stars that were all in the disk, was very much limited by this dust. So rather than just making the stars dimmer for Keptine, it meant that he couldn't see most of them at all. So he would have the galaxy as much too small. So we've explained why Keptine was wrong because of the dust, but we still don't know a reason for that 30,000 there. So why was Shapley so big? And for that, I'm afraid we're going to have to wait for a little bit farther along our journey. So next we come to the galaxy's rotation. So this is one of those things that's actually a lot easier to learn about in other galaxies. So we're sort of stuck in the middle of the Milky Way, looking out through it. And there's no way we can ever get out of the galaxy to try and get a different perspective. But with all of the other galaxies in the sky, we have sort of a laboratory with lots of different specimens we can examine. And we can look at them in a much more sort of holistic way and see the whole galaxy. So this is a picture of the Sombrero Galaxy. And in 1913, astronomers discovered that it rotates. So we knew that other galaxies, they were spinning. So maybe the Milky Way was as well. But to actually prove that would take a lot longer. So in 1925, a guy called Lindblad came up with a great theory that sort of showed that, hey, maybe the Milky Way is rotating. So what he did is he noticed these high velocity stars. So there were a bunch of stars in the sky that were moving very quickly compared to the sun and all of the other stars we could see. But what was weird is that all of the stars on this side of the sky were moving away from us, all of the high velocity stars at least, and all of the high velocity stars on this side of the sky were moving towards us. So that degree of organization in the stars would be pretty crazy. So one way to explain that, or another way to explain that, is that those stars are all staying still, and it's us that's moving. So we're moving towards those stars and away from those ones, which seems a lot simpler. And one way you could have a situation like this is if the sun and therefore the Earth are part of a rotating disk, and these stars, for whatever reason, aren't. So I don't talk a lot about the stellar halo in this talk, but these stars are stars that belong to that stellar halo. So in one of the first diagrams I showed, there was like the disk and the bulge and then a few stars scattered around. But that wasn't really a proof. It was a good way of explaining something we saw, but it wasn't solid evidence. So to get something a little bit more solid, we had to wait a little while for a man called Jan Oort. So I'm going to take a quick physics break. This is the only equation in the entire talk, so if you don't like math, this is it. And I'm actually going to make it a little bit simpler for you to start out. This square root and this g here, they're only used for actually calculating exact numbers. I don't really care about numbers right now, so I can just ignore them for a little while. So what we have is that the speed that something orbits has to do with the mass of the thing it's going around and how far away it is from it. So if you're orbiting something that's really small, you're going to go around pretty slowly. But if you're orbiting around something that's really, really massive, you're going to go way faster. And at the same time, if you have two planets that are orbiting something, say the sun, the one that's closer is going to go faster than the one that's farther out. So we can see this in our solar system. So here we have how fast they're orbiting, and here we have how far they are from the sun, and the various planets. So Mercury is orbiting a lot faster than Neptune. So what Oort did is he extended this to include the galaxy as a whole. So if the center of the galaxy here is here, and we have the orbits of 3 stars as they go around, this one that's closer to the center of the galaxy is going to go around much faster than this one that's far from the galaxy. So let's put this in terms of stars around the sun. So if we have a bunch of stars that are all the same distance from the sun, and the galactic center is somewhere down here, these stars are closer to the center of the galaxy than the sun, so they're going to move faster. And these ones are farther away, so they'll move slower. But measuring actually how fast these stars are moving in any sort of absolute sense is quite hard. So instead, we're interested in how fast they're moving towards or away from the sun, and rather than moving towards and away at all, actually. So these guys are speeding past the sun, orbiting faster. So this one is coming towards the sun, while this one's going away. Well, if we look at those stars that are farther away from the center of the galaxy, they're going to be falling behind the sun. So this one will be moving towards us, and this one will be moving away. So that means if you scroll around the sky, you should see the stars as a whole going from moving away to moving towards to moving away again, and then to moving towards. So Oort was able to predict this motion in the stars, or this behavior. He then went out and he saw just this, exactly as he predicted. And so because he was able to come up with a theory that made concrete predictions and then prove those predictions true, this is considered a fairly solid proof of his idea that the galaxy is rotating, and that this rotating, the speed you're orbiting depends on how far away you are. So great, we have a galaxy, it has a disk, it's rotating, awesome. What about this dark matter halo I mentioned? So now that we know the galaxy is rotating, and we know that the speed is falling off the farther away you get, we can make some predictions. So we can model how fast the stars should be orbiting at a given distance. And you get something that looks kind of like this. So if you notice, these stars in the middle are sort of whipping around the center. Well, the ones at the edge, they're moving quite a bit more slowly. But when we actually look out and measure the speeds of stars in our galaxy, we get a picture that looks a bit more like this. So these stars at the edge are moving much more fast, or much more quickly, than these ones, if you look again. Come on. Yes, they're moving slowly, moving quickly. So that's weird. So another way to look at this is with a graph. So here we have how fast they're rotating and how far they are from the center. And by sort of just the theory that Oort predicted, we would expect a curve like this. So the farther you get, the slower you orbit. But what we see is something like this. So let's go back to our handy little equation for orbits. So we need these two sides to be equal. So the distance is staying the same. So let's just look at stars that, let's say, the radius of the sun. So we can predict their speed, how fast they should be orbiting, but we see it's actually higher than it should be. So the only way to do that, other than by changing the distance, is to change the mass. So because we see these stars moving faster than they should, that means there's actually more mass in the galaxy than we can see. So we call that mass dark matter. Just because we don't know what it is, we can't see it, it doesn't emit light. So dark matter takes up most of our galaxy. So most of the mass of our galaxy is in this dark matter. But actually, the universe as a whole is dominated by this dark matter over the matter we know. So on this pie chart, we have this little blue slice, 4% of the known universe. That is taken up by matter. So that's things like dust and gas and stars and planets and you. Where the dark matter is this purple slice, which is the other 22%. This guy, 74% of the universe, is dark energy, which you have to go farther than the Milky Way to really even start to understand. So I'm just going to leave that as a tantalizing tidbit for you to think about for a while. So whoa, whoa, okay, dark matter, the universe, let's try and get on course. We don't want to get too distracted on our journey. So what have we got to so far? Well, we've seen that the galaxy has a disk, and we know that, but we haven't quite gotten to this 100,000 light years. We're still a little stuck on Shapley's 300,000. We know there's dust, so that's pretty good. And we know it's rotating, so again, we're getting pretty far. And it has a dark matter halo. So what about this bulge? So again, the bulge of older stars. It's a central part of our galaxy. So this is another one of those cases where it's easier to learn about other galaxies than our own. So this is a picture of the Andromeda Galaxy. And if you just look, you can kind of clearly see that the central region is sort of more red than this outer region. So they're two distinct parts. So for the longest time, astronomers would look at galaxies in the sky using blue photographic plates. So this was taking pictures that were only sensitive to blue light. And you can kind of understand why they did that. If you look up at the stars, they all sort of have that whitish blue color. So the brightest stars are in blue. So when you look at Andromeda in only blue light, you get something that looks a lot like this. So for a lot of time, this was all astronomers could see. And they were actually able to make out the individual stars in the disk of Andromeda, which is pretty impressive, really, because this thing is 2.5 million light years away. But they couldn't see the stars in the middle. And that was confusing, and people didn't really have a good answer for that. So at one point, this guy called Walter Bade decided to look at Andromeda using red photographic plates instead. And at this time, these were actually a fairly new invention. And his logic was around, so when I look at Andromeda with my naked eye, the center part looks redder. So maybe the stars there just are the brightest ones are more red. So if I flip between these two, you'll kind of be able to see that the bulge part is much brighter in this image than in the blue, which makes sense. You could see it as red in the earlier slides. But when Bade looked at Andromeda with these red photographic plates, he was able to make out the stars in the center, which is fairly impressive. So that means that the stars at that center are of a completely different type than the stars at the edge. So he found that there are two distinct groups of stars in the Andromeda Galaxy. There are these old stars that are red in the core, and the young ones in the disk that are blue. So the color we showed, they show up in different colored light, so they're a different color. But how does that go to age? So to do that, you need to know a little bit about how stars work. So this is going to be the super quick intro to sort of stellar physics. So blue stars are hot. So they burn through their fuel really, really quickly. And when they're done all their fuel, they die. So you're left with just the red stars that are a lot cooler. They don't burn as hot or as fast, so they last a lot longer. So if you look at a young group of stars, it's going to be filled with these blue, hot, fast-burning stars. But once you're looking at an older group, there's not going to be any blue stars left. So once we've separated these galaxies into two groups of stars, they were actually able to notice that there are two types of Cepheids. So there are these type 1 Cepheids, which are the ones that are found in the young groups of stars. And then there are type 2 Cepheids that are found in older groups of stars. And the type 2 Cepheids are actually dimmer than the type 1s for the same luminosity, or the same period. So now, just a piece of trivia that people were able to work out. These globular clusters are part of the old group of stars. So if you remember, Shapley's model for the Milky Way, 300,000 light years across, to do this, he used globular clusters. And the second step on his ladder was Cepheids. But he used the brightness of those Cepheids from the nearby Cepheids. So he took those type 1 Cepheids, found out how bright they were, and assumed that the Cepheids he was looking at in those globular clusters were the same brightness. So if he saw them as being a lot dimmer, it was because they were farther away. Where if he'd assumed that they were actually naturally dimmer objects, they wouldn't have to be as far away to have the same dimness. So what Shapley took to be 100,000 light years, or 300,000 light years, is actually 100,000 when you take into account that he was using the wrong type of Cepheids right in the very second step of his calculation. So everything else from that, because each rung on the distance ladder depends on the one below it, was similarly shifted away. So great, we finally got into how big the galaxy is. The first step on our journey is now behind us. We don't have to keep having those memories of the first day in the airport. So our bulge, though, is actually really hard to observe. So one reason you can kind of imagine is because of all that dust. So to look through that dust and see the stars there is pretty hard, especially before we were able to use the near-infrared, which, as I showed you earlier, isn't as affected by the dust. But even if we look through the dust, even if we use the near-infrared light, those stars are still super far away. So I don't know if you can see, there's actually a candle there. So as things get farther and farther away, they get so dim you can't see them at all. So it's very hard to observe. So we go back to Walter Bade, the same guy that discovered the bulge in Andromeda. He decided to try and see if he could observe our own bulge. So he looked at a bunch of globular clusters, and he saw one near sort of where they predicted the center of the galaxy to be by looking at how things were rotating. And he noticed that that globular cluster didn't seem to be as blocked out by the dust as all of the others. So he thought maybe that would be a good spot to try and look through where there isn't as much dust to see the bulge. So he looked there, and he saw some of those type 2 Cepheids. So that meant that he was able to get a distance to the center of our galaxy. And also, because he found the type 2 Cepheids that are in the older population, rather than the type 1s that we know to be in the disk around us, he was able to show that at the center of our galaxy, there is this collection of older stars, like in Andromeda. So looking at these stars in the center of the galaxy is something that astronomers are still really interested in today. And with the modern technology and some of the best telescopes, we're able to look at them very closely and actually watch them over time as they move. So these stars are flying around super fast. So this video is going over, I think, about 10 years. And this star here manages to go all the way around in orbit. So in comparison, it'll take the sun 200 million years to get around the galaxy. This guy does it in 10. So if you remember, again, our familiar little physics equation here, we can measure the distance those stars are from whatever they're rotating. That, I just want to point out, you can't see anything here. So this is like a little star that somebody put in for fun, but there's nothing that we can see there in our real telescopes. But we know those stars are orbiting. So we know their distance, we know how fast they're going, that we can just see and measure. So using that, we can calculate the central mass. We can calculate how much that thing they're orbiting around weighs. And when we do that, we get that it's 4 million times as heavy as the sun. And all of that mass is in this teeny space within this orbit. So this star's orbit is about the same size as our solar system. So that's a very small space to have 4 million suns inside. And so the only way you could have that much mass in that small space is to have a black hole. So that's pretty cool. The bulge at the center of our galaxy, the center of that bulge is a black hole 4 million times as heavy as our sun. So we've gone through most of our journey now. We're at the last leg, and what is perhaps the most interesting, where we notice these spiral arms. So they're very iconic of the Milky Way. I suspect a lot of you, if I asked you to close your eyes and imagine what the Milky Way is, or it looks like, half of you might come up with an image like the one I showed on my earlier slides, with the tree and that smear of stars across the sky. But I bet at least half of you would come up with a picture like this, where we have this disk with the beautiful spiral arms. But of course, that's kind of hard to observe. We're stuck in the middle of the disk of our galaxy, and the best and brightest pictures we'll be able to get are like this. You can kind of see maybe a disk, you can maybe see the bulge, but can you tell there's spiral arms there? You really can't, not easily at least. But this is another case of where we know much better about other galaxies. So Andromeda, for example, we've known that it has spiral arms since 1887, which is a fairly long time ago when you consider that Keptane was only measuring the size of the galaxy in sort of 1903, I think it was. And it would take a lot longer to know that the Milky Way had spiral arms. So for a long time, people knew, okay, Andromeda has spiral arms, maybe we do too. So they would try and measure this. So they would look at the stars around the sky and try and figure out how far they are, using methods that I've talked about already. But these methods aren't very precise, so their numbers would have lots and lots of error, and they would just get things wrong. But by looking at other galaxies, we realized that the spiral arms are where stars are being formed. So we've already talked about the fact that they're filled with these young blue stars, but they're also filled with these giant clouds of dust and gas that are the sites of star formation. So these are the same clouds that we saw earlier in the molecular hydrogen that form this thin band through the disk. So this guy called William Morgan decided to take advantage of this. So he knew that these clouds of star formation were in the disk. And even better, he knew that they were in the spiral arms from looking at Andromeda and other spiral galaxies. So rather than looking at the positions of individual stars, he looked for these gas clouds. And each of these clouds had a bunch of stars in it. So he knew that, like Shapley knew that all of the stars in his globular clusters were the same distance, Morgan knew that all of the stars in these gas clouds were about the same distance. So he could make the same measurement a bunch of times. And by repeating the measurement, he was able to get a lot more accurate distances than anybody else before him had for stars in the disk of our galaxy. And he was able to see something a little bit like this. So where you see there's a bunch of the clouds and stars clustered close to our sun, and then sort of a dark spot where there's not as much, and then a bunch more again. So this diagram shows 3 spiral arms. Morgan was only able to see 2 in his work, but that's still pretty impressive. So he was able to show that our galaxy is a spiral galaxy, which made everybody happy because spiral galaxies are the most beautiful, and we're all a little vain. So what causes these spiral arms? It's actually a question that we have astronomers as a whole are still arguing about a little bit, which is pretty crazy. So one way you could think about it is that it's like a pinwheel. So you have sort of these solid arms that are trying to rotate around with the galaxy. But we already talked about the fact that stuff farther out is rotating more slowly. So this is a pinwheel where the tips of each of the wings is trying to go more slowly than the middle. So you kind of imagine that's not going to go too well for the pinwheel. So this is a video of a galaxy spiraling with sort of the solid arms like in the pinwheel. So as you can see, the edges are going much more slowly than the middle, and the thing is winding up, sort of like thread on a spool, getting tighter and tighter and going around more. So if this was how spiral galaxies worked, we wouldn't expect to see these spiral arms at all. We would just think we'd see things more like this, and less like those beautiful, loosely wound galaxies we see all over the place. So that's not quite a good picture to have in mind. So instead, it's good to visualize something more like a traffic jam. So in a galaxy, we call this a density wave. But the premise is, you're on a highway, all of the cars want to travel at a given speed. But there's this pesky brown truck that just wants to go too slow. So he gets this collection of cars behind him. And so behind the truck, you have an overdensity of cars. There's too many cars there. But eventually, those cars will be able to pass the truck and move on. So here, we have these 4 cars, red, blue, purple, white. And those same cars, later, have worked their way around the truck. So we have the red car, the blue, the purple, and the white. They've gotten back to their normal speed. They've spread out again. But in the time that they've gotten around the brown truck, more cars have piled up. So there's always that cluster of cars behind the brown truck, even though it's not always the same cars. So in galaxies, we see a similar thing. But there's no truck in the galaxy. There's not a wall holding the stars back. So the actual cause of these density waves, the actual astronomical equivalent to the brown truck, is the thing that astronomers are still arguing over quite a bit. We're pretty sure that it's caused by density waves, that this picture is right. It's just the cause that is a little bit unclear. So this is another video similar to the one I showed before. But rather than having the spiral arms rotating like a solid body, like a pinwheel, they're this density wave. So if you watch carefully, you should be able to see individual stars going towards the arm, then they cluster up and there's a bunch there, and eventually they'll pass out again. So the speed that the arms are moving isn't the same as the speed of the individual stars that make it up. And this allows for spiral arms that last a lot longer and are a lot more stable than in the other the sort of solid rotation like a pinwheel. So we've reached the end of our journey. We've seen their galaxy is a disk that's 100,000 light years across, and we're sort of near the edge of it. We've seen that this disk is filled with dust that form both these brilliant, beautiful, bright clouds, and also that just form a haze between us and stars, making them harder to observe. We've seen that the galaxy is rotating at 200 kilometers a second. It's spinning super quickly. We've seen that it has a dark matter halo from this rotation, that it's made up, that most of the galaxy is made up of a type of matter that we can't hear or see or taste or smell, that we can only find via gravity. We know that it has a bulge of older stars that are redder and all near the center. And we know that it has these beautiful spiral arms. So next time you're presented with a view like this of the galaxy on a dark night maybe, or even next time you just see an artist's impression of what the Milky Way looks like from afar, maybe you'll have a slightly better idea of what the galaxy actually looks like, the parts of it, what it's composed of, and how we knew all of that, which was a fairly epic journey in of itself. So thank you very much.
So we have a few minutes for questions. Do we have some? Right here.
So you mentioned that there's the stars, like the bulge of older stars, so it's like and the younger ones. So it's kind of what makes it so that all the older ones congregate in the middle and the youngsters all on the outside?
Yeah, so that's actually a pretty good question. So that comes down to how the galaxies actually formed. And it's another one of those topics where there's still some arguments among astronomers. So I'll just show you sort of one of the pictures we have, is you have a big cloud of gas that slowly collapses to form a galaxy. So it sort of starts forming stars, and it's still the sort of spherical lump. But eventually, as it collapses, it'll form a disk. And in that disk, that's where the rest of that dust is going to lie. So all of the stars that are formed later will be formed in that disk. But all of the stars that came first when it was starting to collapse, those are those older stars that are in the disk, the bulge.
So the ones near the end of their life and starting to turn red are the ones that are
again, so what I was mentioning earlier, the older ones, all of the blue stars would have died off already. So you're just left with the ones that were always red.
Lower mass, not the red supergiants?
Yeah, the lower mass stars are the ones that are left. So those are the ones that are cooler and red.
Red supergiants are also old.
Yeah.
Red, but high mass.
But it's true, but those ones don't last very long, right? They still die really quickly.
Oh, so that kind of red star, because I was thinking the red supergiant.
No, yeah. So these are older, cooler, younger, lower mass stars.
Oh, I see. Thank you.
Here?
Sorry, I don't think we're going to be able to hear you for a sec. Okay, shoot.
When things orbit other things, why is it because of how far away they are? Why don't they just go at different speeds?
So if you have two things at the same distance around the same star or the same anything, they're going to move at the same speed. And that's just because of physics, really. There's not a lot other than that. It's something that we can calculate quite precisely, and the distance is just one of those important parameters. I'm not sure if that was sort of getting at what you were asking.
I think so. Does it have to do with the mass of the...
Oh, the actual thing that's orbiting? No. So if I'm orbiting around the sun, my mass doesn't have anything to do with how fast I'm going to go around, just the mass of the sun. It's kind of like if you drop a feather and a bowling ball, they'll both fall at the same speed, other than, that wind and stuff will move the feather a lot more.
Question in the back? Right here?
Do we know what shape the Milky Way is going to look like in a few more trillion years?
Sorry, just the shape of the Milky Way?
Is it going to become more army or less army?
Oh, geez. So how it's going to change? So that's actually one of those questions that is hard to answer because astronomers are still arguing about it a little bit. Actually, knowing how galaxies change over time is pretty hard to do because they change so slowly that we can't look at the Andromeda over the sort of 200-300 years we've been able to see it and see it change at all. So it's hard to figure out what galaxies looked like in the past and what they're going to look like in the future. But at least on any perceivable time scale, the Milky Way is going to stay the same. And eventually, actually, we know the Andromeda Galaxy is going to hit it. And that's going to cause everything to go very different.
What are they speculating could be the brown trucks?
Yeah. So a lot of the problems with that is that a lot of the things we think would cause that would only cause spiral arms that don't last very long. So one thing is that there's always other galaxies and other smaller things around. So the Milky Way, we have the Magellanic Clouds, which are big, well, big-ish dwarf galaxies that are orbiting around us. So one of the ideas is that other stuff causes the gravity of the disk to be sort of deformed, and that causes the sort of this density wave to form. Sort of like if you drop a pebble in a lake, you're going to get the waves coming out of it. But it's not a perfect theory.
In the back.
So with this density wave, we know that almost all galaxies have a quasar or a black hole in the center. Assuming that has particularly probably a lot to do with the rotation of the galaxy in some way. Correct me if I'm wrong.
I don't actually think that any sort of black hole at the center would make a difference at all to the rotation or the... I mean, it's entirely possible that if the black hole's rotating, it might be rotating in the same direction, a lot like how the sun is rotating. That wouldn't really have, I don't think, an effect on that. It's gonna, again, like those central stars we were looking at, the way they're orbiting is entirely because of how much that black hole weighs, but that's not gonna directly influence spiral arms. So are you saying that matter is being formed by the black holes? I don't know, maybe we should talk after. I'm not quite following.
Yeah, here.
Since there's a black hole in the center of the galaxy, and light gets swallowed by black holes, and why is the center so bright?
Right, so you've hit a topic. So when light falls into a black hole, it can't come out. But it's not going to suck all of the light from around it into it. So if you're standing near a black hole shining a flashlight out, that light isn't really going to circle back and fall in. It's still going to escape, and we'd be able to see it. So the center is really bright because there's lots of stars there, for one thing. But also there's a lot of dust and gas that the black hole's pulling into it. So actually, if you look at sort of the similar view that I was showing you with the stars orbiting around, if you look at that with an X-ray camera, you see this just big cloud of bright light, which is from gas that's falling into the black hole.
In the middle, here.
Yeah, you said many different galaxies have spiral arms.
Yeah.
Are they all rotating in the same direction?
So rotating in the same direction is kind of something that doesn't make a lot of sense because they're all oriented in different ways, right? So when I showed you the picture of Andromeda, we kind of see it looking down on the disk. But with the Sombrero Galaxy I showed earlier, we're looking from the side. So if you were to look at it from the top or the bottom, the Milky Way is rotating in a different way. But one thing we do see, if I can try and point it out, is, oh, do I have a good one? Well, this is, yeah. So let's say, I'm not actually sure which way the galaxy is rotating. I should be able to say that. But I think it's going this way from this view. So if you notice, the galaxy is rotating around this way, and these spiral arms, they're pointing opposite to the way that the galaxy is rotating. And that we've been able to see is fairly constant between all of the spiral galaxies. So the arms are pointing sort of behind the direction of rotation rather than leading.
So the only difference would be in just the different positioning of the galaxy.
Yeah, I guess.
So I guess I just rephrase a little. So basically the idea is all the arms appear to curve outwards in the same direction.
Curve outwards. So relative to which way they're rotating, the arms sort of have the same shape.
You don't have arms that form a U.
No, they don't. So they're all going in the same direction.
So it's like,
but also, yeah, so if this was a picture of another galaxy and it was rotating the same way as ours, you would expect the arms to have the same general, they might be more or fewer, but they would have that same sort of shape.
Okay, let's just have a couple minutes so that people can get to their planetarium shows. Yeah.
Generally, the thought is that the universe is expanding,
Right.
but our galaxies are not. Or
Yeah.
are they?
No, they're not. So the universe is expanding, but the galaxy is being held together by its own gravity. So if for some reason you were to be in a box a room or something and the room was getting bigger, even though the room's getting bigger, it's not necessarily going to pull you apart. You're being held together by, you know, sinews and bones. So in the same way, the galaxy is being held together by its gravity. And actually the whole local group of galaxies, so I mentioned the Magellanic Clouds and Andromeda, there's strong enough gravity between them as well that as the universe expands, they're going to stay with us.
A supplementary characteristic is that we have a sphere, or not a sphere, sorry, we have a disk.
The galaxy?
Our galaxy,
Yeah.
the Milky Way. Why is it, what's the cause and effect? Is it because it's spinning? Or is it just because it is what it is?
So
isn't it a
yeah, so disks are one of those shapes that, like gas and dust especially, really likes to form if it's spinning. It has to do with sort of momentum and energy, and if you form a disk, it's sort of the state which is most stable and can maintain that momentum and energy that you had when you started. So it's mostly because it's spinning, it forms a disk.
That's the cause and effect. Why isn't it a sphere?
Because it's not as good for that. You can't keep the same momentum and energy in a sphere. So if it was collapsing, it has to go faster if it was a sphere, and things just don't work out. So it naturally wants to form a disk.
Are there spherical galaxies?
Yeah, but they're not spinning. Or not as much.
Okay, last quick one. Yeah, stay quick.
It's like the black hole in the middle of the galaxy causing it to spin, or is it spinning because it's what's collapsing inwards?
So the black hole has nothing directly to do with the spinning of the galaxy. So that really comes from if you have a cloud of gas. So I was sort of mentioning earlier an idea of how galaxies form. So you have this giant, giant cloud that collapses. And sort of like how a figure skater, if she puts her arms out and becomes bigger, she rotates slower. As it falls in, any tiny, tiny amount of rotation it might have had gets amplified. So then the black hole might form afterwards, but it really doesn't have anything to do with the rotation.
Okay, do we have the end slide?
Oh, yep, it's the other.
Okay, we just have an announcement. So now we have planetary
Nope, not that one.
shows for those who signed up online, and you can meet at your planetarium
Yeah.
times, so that will be on your ticket. At the lobby, right in front of the elevator. So if you just go out these doors, you pass 2 sets of doors, you'll see some couches in front of the elevators and a sign. So meet there about 5 minutes before your scheduled time, and someone will come to meet you. Are they here? One is Nathan, who's sitting by the camera, will come to meet you and take you to the planetarium in the other building. And the telescopes will be open for the next about an hour and a half, and you can get to them by going up the elevators to the 14th floor, making a right, taking the stairs up to the 15th floor.
There's signs, probably.
There's signs. All right, have a good night, everyone.
Hey.
Have your lecture slides?
Oh, sure. Let me just try and find them.